Okay, so we're jumping back to chapter 2 for a minute to talk about systems of equations, which I feel like we've done already, but a couple things that we didn't talk about were other ways that we can have solutions. And so remember that a system of linear equations are two or more equations, I should say equations, in two or more variables. And we talk about like that meeting point, right? Like the break even point, we're talking about cost and revenue, the equilibrium point, where does it balance out? And so remember that a solution to a system is where they're true at the same time or where they intersect if we talk about graphing. And so all the ones we did from chapter 1, they all worked out really nice, right? Like if we had two lines, two linear equations can cross in at most 1 point, right? So like one thing that happens is what we've seen already from chapter 1 is that there might be one solution. What else could happen? Well, remember that sometimes they might not ever cross, right? If they're parallel lines, then they're never going to intersect, and you might have no solution. And then the last thing that can happen is when they're the exact same equation, right? And if you graph the exact same equation twice, they intersect at every point, and we say that that is infinitely many solutions. So we're just going to practice again some more graphing for as we get into more complicated things. So again, hopefully this will be a nice review for you. So again, just like the quiz we just took, we want to be able to graph these. So step 1 is I'm going to put it in slope-intercept form. So on the top one here, I'm going to subtract 2x over, and I'm going to divide by -1, which makes that 2x minus 1. So that's my y-intercept of -1. I'm going to go up 2 over 1. I'm going to try to make a nice line. We'll see if they intersect nice or not. And then if I switch colors here so we can follow what I'm doing, I'm going to subtract 3x, and I'm going to divide by 2, and I get y equals -3/2 x plus 6. So now I go 1, 2, 3, 4, 5, 6. And I go down 3 over 2. I always like when that happens because I can see very nicely, just like the ones we've already done, that the solution of that is right where they cross, which happens to be at, 2, 3. And if you plug 2, 3 into both of those, you would get a true statement, right? Okay. What about this one? Again, notice the top equation staying the same. So this was y equals 2x minus 1. Same one as last time. But now on this one, if I subtract 6x over and divide by -3, I get y equals 2x minus 1, which means when I graph that at -1 up 2 over 1, it's the same equation, right? Just written in a different form. When I put it in slope-intercept form, it's the exact same, which means that my answer to this is going to be that every number works. And what we say in math class is infinitely many solutions. And my last one here, again, same problem for the top, that this is going to be 2x minus 1. So my minus 1 up 2 over 1. And on this one now, if I subtract 6x over and divide by -3, I get y equals 2x minus 4. So now I have a y-intercept of -4 up 2 over 1. And so because they have the same slope, because they have the same rate of change, they're never going to meet. And so the solution to that is that there is no solution. Okay? So it says, consider a system composed of two linear equations and two variables. Can the system have exactly two solutions, exactly 3 solutions, exactly a finite number of solutions? What do you think of that question? We kind of just talked about this, about how many solutions can they have. So I want you to think about the answer to that and maybe type it in. We'll look at it in class. And then also look at number 2. It says, suppose at least one of the equations in a system composed of 2 equations in 2 variables is nonlinear. Can the system have no solution, exactly 1 solution, exactly 2 solutions, exactly a finite number of solutions, infinitely many solutions, and illustrate each one with a sketch? Well, you can't really illustrate this on Edpuzzle, but I want you to think about the answers to these questions, and we'll share this in class, okay? So we can talk about nonlinear equations. That's kind of what that was just about. But what we really want to talk about in this class is, what if there were more than 2 unknowns, right? So 2 unknowns in 2 variables, we have 2 equations. What if you had 3 equations with 3 variables? Well, if you start talking about 3 equations, like x plus y plus z equals 2, you're talking about a 3rd dimension. So like xy plane is a flat plane, xyz plane is 3-dimensional. And so you can still have the same kind of picture, but now they're planes instead of lines. So if you have 3 equations in 3 variables, they could all meet in like one specific point and have one solution. You also could get infinitely many solutions. And so if you have 3 planes that intersect in a line, that line keeps going forever, just like the planes keep going forever. And so that's infinitely many. And you could also have no solution, where the planes are all parallel. So you can have the same idea. But for every variable you add, you have another equation. So if you have 3 variables, you're going to have 3 equations. If you add 4 variables, you're going to have 4 equations. So that's kind of something to think about, that every time you add another variable, you add another equation to the system. And so I want to do one with 3 variables here with you. This is one we're going to start in class, but I want you to think about what our variables would be, right? A farmer has 200 acres of land for cultivating crops A, B, and C, and the cost per acre is $40, $60, and $80. And they have $12,600 available for land. And so think about, like, if A is crop A, B is crops B, and C is the number of acres you're going to do crop C, I think right away we can think of 2 equations talking about the total number of hours versus the cost. But also notice that each acre of crop A requires 20 labor hours. Each acre of crop B requires 25 labor hours, and we have a total number of labor hours. And so it says, if she wishes to use all of her cultivatable land, the entire budget, and all the labor available, how many of acres of each crop should she plant? Formulate, but do not solve the problem. So see if you can come up with your 3 equations using A for the number of acres of crop A and so forth. And we'll start here in class, okay? Eventually, we're going to be solving problems like this.